Hello everybody, welcome back. Today we're going to be discussing the solution to the Laplacian in cylindrical coordinates with no z dependence. Let's get started. So when are we going to be using these solutions? Well, let's consider a cylinder that's very long, and this Laplacian could be maybe thought of as or this v can be thought of as the electric potential. So we're solving for the electric potential in space, pretty much, all the regions. So let's say there's no z dependence. What does that mean, right? Well, that just means that it's symmetrical about the z-axis. So we can consider these cylinders to just be like, we can consider them to extend infinitely in every direction. That way, there's no z-dependence at all. In physical applications, this just means that maybe we are working with, near the center of the cylinder. So obviously, there's going to be z-dependence closer to the top and bottom. However, near the center, the z's are sort of going to cancel out. And so the z dependence is going to be negligible around this region. But that's also another case we can use it for. But it's very easy to just pretend the cylinder just extends to infinity. That way there's no z dependence. So it is actually very useful in physical applications. Just like you can ignore air resistance sometimes if it's negligible, even though it is technically there. It's just negligible, so we don't account for it. Okay, let's get started. So in order to solve these partial differential equations, the most popular and probably the most useful method would just be separation of variables. So what we do is just assume that v is equal to a function of s times a function of phi. So this is what we assume. Obviously not every solution is just going to be a product of s and phi. However, the solution that we do get is very special, and a lot of times we can fit boundary conditions onto the solution that we'll get using maybe like Fourier series and stuff like that, using these special functions. Like for the spherical case, you'll get Legendre polynomials, which have nice orthogonal properties, which allow you to fit boundary conditions very easily, or much easier than, I don't know, say some other solutions. But in general, PDEs are very hard to solve because they don't have a closed form solution like ordinary differential equations where you just fit like two arbitrary constants. No, the arbitrary constants sort of become boundary conditions. And in order to produce a unique solution, you need to fit those. You need to define specific boundary conditions in order to get a specific solution. So partial differential equations are really cool in that respect, in that the fact that they don't have a specific form. They can be really anything. But what we're gonna do is assume this form here, and you may ask like, well, if there are other solutions, why are we just assuming a specific form, right? Well, it's sort of like the analogy. I remember watching a YouTube video, like some guy gave an analogy. Andrew Dodson, yeah, he was a physics guy. He studies. I mean, he's a PhD student at a university, but basically, he said that it's like sort of looking for your keys out in the dark, right? So you might as well look for your keys underneath a streetlight, right? And if it's not there, then well, you just can't find it. So if we can't find the solution, or we can't fit the boundary conditions using separation of variables, then I guess we're just not finding the partial differential equation, because good luck solving this for other cases, right? Alrighty, so let's get started. So no z dependence, so just a function of s and phi. So what this is going to get us is, when we substitute that in, these partial differential equation or partial derivatives are going to turn into ordinary derivatives, because in the eyes of the s, this is just going to be, the g is just going to be constant. So we can just factor that out. And what this becomes is an ordinary derivative. And this is not v, this is f. Sorry, I'm already messing up. I had like 240 milligrams caffeine. Well, I'm drinking an energy drink with that much caffeine in it. At 1:15. I make a good decision. Alrighty. So in the eyes of the f, or eyes in the I, holy crap. This is very wrong. Hopefully I don't have to restart the video. I'm hoping you know that that was phi, right? You guys are familiar with the Laplacian cylindrical coordinates. We're just solving it. So in the eyes of the phi, this is just going to be, s is going to be constant, and what we're going to get is a total derivative of g with respect to phi. And in the eyes of the z derivative, since we're not assuming any z dependence, this is all just a constant. So this term is just 0. You can ignore that. And you can see that if we ignore this term, it's actually going to make this much easier to solve. I'm not entirely familiar with how you would solve it with z dependence. I'm an undergraduate student, so I'm not pretending like I know how to solve this for all possible cases. Alrighty. So here we have the total derivative form, and what we're going to do now is just divide by v both sides, and we're also going to divide, or we're going to multiply by s. So we're going to multiply by s squared, and we're going to divide by v. So I guess that's what we're doing here. So what we get is s over f d ds s this, and then on the second term what we're going to get is just 1 over g, and this is all equal to 0. So now you can see that since f is a function of s, I'm assuming you know that you know how to correlate, right? So f is a function of s, g is a function of phi. So this term is just a function of s, and this term is just a function of phi. And so this next step is going to be a little bit hand wavy, not really a proof, but when you do separation of variables, this is usually the point you get to. You have a term with the function of s, term with the function of phi, right? So the idea is, since both of these terms have to equal 0, these terms can't individually depend on phi, right? They have to equal some constant, because this is going to be the only way to cancel these terms out. So let's say we call this plus k, and this term is going to be negative k, right? This is what these terms are going to be equal to. Well, in that case, they're always going to cancel, right? But if this term was a function of s, think about how are we going to cancel this out with a function of phi? So I don't know. We'll call this r of phi. I don't really care what the variables are. I'm just showing you the point. H of s plus r of phi. So how are we always going to cancel these out to be 0? This is just a function of s. This is just a function of phi, right? This, let's say this was s squared, and this, like, I don't know, how would you cancel this out? You can't. So that's the idea. As I know, it's a little hand wavy, but you can also think of it as just maybe we're just considering a special case of these solutions where they just happen to equal constants. But it really is true that we can only have these be constant. We can't have these be functions of s and phi. So that's going to be the hand wavy step out of the way. What we're going to do is actually call these constants. We're going to square these constants just for convenience. You'll see later on, and you can see that it's kind of arbitrary what we associate these constants with, right? This could be negative k squared, and this could be positive k squared. However, you'll see that in the future that if we call this negative k squared, the solution we get is just going to be much more practical, because otherwise we have phi is an exponential function rather than a phi would be some trigonometric function like cosine and sine. And typically when we work with angles, we're going to be working with cosine and phi. So the exponential solution isn't really going to be very valuable to us. But the trigonometric solution is very practical. So we're going to call this positive k squared and negative k squared. Alrighty. So we're just going to equate those terms. I'm running out of breath. But yeah, it's going to be quite a bit of a video. I'm practicing to tutor in the future, so I want to get like really good explaining stuff. That's why I make these videos. So we get s ds s is equal to k squared f, and then here we're just going to equate this to negative k, and we're going to move the g to the right side. So that's what we did in this first step here. So d squared g phi squared is equal to negative k squared. So there we go. These are going to be the two differential equations we solve. We have to find f, and we have to find g. We know based off of our initial assumption that v is just equal to the product of these two functions. So there we go. We just reduced a partial differential equation into two ordinary differential equations. So this one is going to be pretty trivial to solve. I'm assuming that if you know if you're studying Laplacians or partial differential equations, that you know this differential equation pretty much by heart. So we're not really going to worry about that. You know the solution to this one, right? But this one might be a little trickier and might be a little unfamiliar to you. This is called the Legendre linear differential equation. Legendre linear. And this is actually not just the Legendre linear. This is a special case of the Legendre linear differential equation, which is going to be called Euler's linear differential equation, which I know is really confusing because the Legendre equation is a completely different equation that produces the Legendre polynomial. So let's not confuse it with that. An Euler's linear equation, it could just be really confused with other famous equations under his name. He has a lot of equations under his name, okay? And he's pretty much in every branch of mathematics known to man, okay? So just don't confuse it with that. But in the end, just know that this is a differential equation that has been studied, that you will go over in an ordinary differential course, and it has a pretty easy solution, or an easy way to solve the solution. So if you try to solve this yourself, it might be a little difficult because there is a certain trick that might be a little hard to spot. So let's just expand that first differential equation out. So if you do that, you just get this. Is all equal to k squared f. Like I said, this is a well-known differential equation that has been studied, and this is a very particular easy differential equation of Euler's, because we're going to see that the first derivatives are going to cancel out after we make a substitution. So it's going to make this trivial. However, the trick is just going to be defining s as some parameter e to the t. And then we basically just write this all as derivatives with respect to t, and you're going to see a lot of cancellation. So it's much easier to solve f with respect to t than it is for s in this case, and then we just substitute that s back in. So let's do that. So what we're going to do first is just solve this. So what we're going to do is take the derivative of t with respect to s, and you'll find that this is equal to negative t, which we're going to be using. So just take the derivative of s with respect to t, and then just flip it e to the negative t. Remember, if you flip the derivative, it also flips the answer. So you can treat differentials as kind of numbers in this case. I know it might, I don't know, I might trigger some mathematicians out there, but I mean, I'm a physicist. I'm just going to do what I want here. All right. Then what we're going to do is define these operators with respect to t. So first, we're going to try to find the operator with respect to s as an operator with respect to t. And I'm going to actually write this so I don't confuse the heck out of you. This is going to be the same thing as dt, ds, d over dt. This is just a chain rule. Every time I do the chain rule, I always just think, like, how can I make the differentials cancel so just get d over ds? And that would be an actual proper chain rule statement. I know I just triggered a bunch of mathematicians out there, but I'm going with it because it's much, for me, it's just really easy to think of chain rules that way. All right, so we know what dt over ds is. We just figured that out. So what we just did is figure out an operator with respect to s as an operator with respect to t. And so this first derivative here, you can just think of plugging in an f, and that's going to be the derivative with respect to s. Now, of course, we need to figure out the derivative with respect to the second derivative. So how do you use second derivatives? So if you're not familiar with operator calculus, is just going to be the same thing as ds, right? The derivative with respect to s acting on itself, which we know is just that. So we just have this acting on itself. There you go. D over dt. And so I know you guys can tell, but anytime I go like towards the edge of the board, it's much harder to write, so my handwriting just kind of poops out. I apologize about that. So that's why I have to scroll down. So what we're going to do, what we're going to get is e to the negative 2t times the second derivative with respect to t minus e to the negative 2t times the first derivative with respect to t. Alrighty, so this is going to be the second derivative with respect to s. Remember, so when we act this derivative twice on any function, you can just think of putting an f in the placeholder here, in the blank. So now all we do is just substitute these two identities in, so this one and this one, into this equation to make it all in terms of t, and also substitute the s in. So what we're going to do is get e to the 2t, because right, s is equal to e to the t squared e to the 2t. And then I'm just going to skip some steps here, because if we just put in an f here, right, then what we get is, as you can see, we have e to the 2t's here, and then we're multiplying by e to the 2t. So this is all just going to cancel. And that was the whole point of the substitution. That's the brilliance of this substitution here. What we're going to get is just d squared f d squared minus the f. That's going to be the first term. And then the second term is going to be the same thing. See, s is equal to the e to the t, right? S is equal to e to the t, and df ds has a factor of e to the negative t, which is going to cancel out. And all we're going to be left with is df dt. And this is all equal to k squared, or f. And as you can see, these terms just cancel. And what we get is just an exponential differential equation, right? This should be pretty easy to solve. So f with respect to t is equal to some arbitrary constant, kt, plus some arbitrary constant e to the negative kt. So once again, if you're studying Laplacians, you should know this differential equation by heart. That's what I'm assuming. I'm sorry if that offends you if you're not there yet, but like, just know this is a well-known differential equation. This is a solution to it. You may look that up yourself. Alrighty. So now, this is a function with respect to t, but of course we have to find the function with respect to s. And luckily, I mean, if you think about it, e to the kt is the same thing as e to the t, the power of k, right? Those exponents just multiply. And we know what e to the t is, right? So this is, all in all, in terms of s, is going to be c1 s to the k plus c2 s to the negative k. And there you go. You have our solution to the differential equation in terms of s. So that's going to be the answer to the Legendre linear differential equation, or Euler's linear differential equation, special case, using the substitution, the trick, which I definitely did not come up with myself. It was just, I looked it up, okay? I'll be honest, I looked it up in my math textbook because I don't know how to solve these differential equations. So, and then of course the second one has a very well-known solution. So all in all, we know what f is, we know what g is, hopefully. And so what we're going to get is, finally, s phi is going to be the product of f and g. Get rid of that. So what we get, and I'm going to rename those arbitrary constants to a, b, c, d, just for convenience. S to the negative k. Then we get c cosine k phi. So this is g now. So this is what we found to be f. And this term is what you'll find to be b. There are going to be two arbitrary constants, c and d. And once again, I'm hoping it's a well-known differential equation to you. You should know it by heart. As this will be g. So there we go. We have a solution to the differential equation. Now, of course, we solved it for arbitrary k. And we can pick these k's to be absolutely anything we want. However, for convenience, it's much easier to work with integer multiples. Once again, this is all for practicality purposes. I mean, I guess you can say, you know, all k's are the solution to this. But for convenience, for practicality, we're going to call these k's to be just integer values. So what you get, these k's are integer values, is we can expand this out into a more general solution where we're summing a bunch of different values of k. Because, right, Laplacian is going to be a linear differential equation. So you have v1 solve this equation and v2 solve this equation. Then their sums, right, if we act a Laplacian on it, it'll just distribute, and all in all is all equal to 0. So a linear differential equation just means that if we have two solutions, we can paste them together to get another solution. That's what we're going to take advantage of here. So we might as well, let's see here. So we can work with k's equals 0, but what about negative k's, right? Let's consider that. Well, if negative k is going to be the exact same thing, it's redundant, because if you plug in negative k squared, that's going to be positive k squared. Negative of negative k squared is going to be negative k squared. So it's just redundant, so might as well start as k equals 0. But we're only going to be working with integer multiples because, right, s to like some fractional exponent, I mean, it's going to make things more trickier, so just ignore those. And what we get is we can have these arbitrary constants to be absolutely anything we want. This is why there's no closed form solution for partial differential equations. Look how much, like, we can work with infinite terms here with infinite arbitrary constants. So that's the thing with partial differential equations. It's all about boundary conditions. Boundary conditions are much more complicated, but all in all, there's going to be one solution for the cylindrical case, right? Using separation of variables. But there are many, many different cases to consider. But this one just happens to be very convenient for a lot of physical problems out there, especially for solving the electric potential in regions, or maybe solving the temperature of some material after a very long period of time. The Laplacian will also, this solution will also give you the answers to that. So what the temperature settles to, right? So here we have the almost full solution. I have neglected some things, right? So when we're working with electromagnetism, right, but not, and we have some line charge, which we'll call lambda, we know that this V is going to be proportional to some LNS. I mean, I'm not assuming you know that, but we do get cases where if we work with infinite line charges or infinite cylinders of uniform charge distribution, the potential is going to be proportional to the natural log of S. That's just because the electric field has to be proportional to the 1 over S, right? Because E is equal to the negative gradient of V. I'm not assuming you know that. This is not an electromagnetism course, but I'm basically saying that we have some missing terms here, right? This doesn't account for every possible solution, because we are missing the natural log, for example. So where is that? Well, when we start at k, like let's just plug in k equals 0 here, and we can see that k equals 0 is just going to produce a constant. Actually, 3 different constants. It's going to produce a naught plus b naught and c naught. So it's all going to be constants, a little redundant. And that's kind of what we're missing here. When we plug in k equals 0, that's actually a special case of these differential equations that we haven't accounted for. When we're applying this general solution, it sort of ignored that special case. So what we're going to do is just solve the special case for k equals 0. What we're going to get for this first differential equation is this. Whoops. Alrighty. So we get df ds is equal to 0. And as you can see, this was actually very easy to solve for the special case of equals 0, because we can just cancel that s. Then we can integrate, divide by s, and integrate. You can do that yourself. So it's pretty easy to see that f of s is equal to some a naught plus b naught ln s. And we're going to call these a naught plus b naught because you'll see why. So this is actually our missing solution here for k equals 0. And then we actually have another special case for the g, which is kind of funny. This is what a lot of textbooks neglect. So if we set that to equal to 0, we get g of phi is just equal to c naught phi plus some arbitrary constant, but that's kind of redundant because we're going to already have a constant here. So we just have some phi here, c naught phi, which is really weird because you don't really see this, but this does indeed produce an equation with a Laplacian of 0. And it does produce some interesting electric fields. If you're interested in that, like this electric field, which is kind of curly. I don't know, let me do some background stuff here. Let me just kind of reduce this. There we go. So as you can see, the electric field that it produces is kind of very curly. And it indeed has a Laplacian of 0 everywhere. I'm not entirely sure what charge distribution makes this, but I mean, we might as well include it in because it's an interesting term, and you can just neglect it for most cases unless you need it. I'm not like, I don't know, it baffles me that this term isn't included because it's kind of interesting for me. Alrighty. So these are the special cases, and then we're just going to include this into the k equals 0 because, like I said, k equals 0 is just a constant, so it's redundant, so we might as well start at k equals 1 and include all this. Alrighty, deep breath. Last equation, no z dependence. The solution to the Laplacian is going to be a naught plus b naught ln s, the full solution that we may utilize to fit whatever boundary conditions, and we might as well include this straggler term here. I find this term very interesting. You're probably just going to ignore it, but I mean, don't hurt its feelings. Don't ignore it. Come on, use it. Alright, so this would be the general solution. And then we're going to multiply our ck cosine k phi plus dk sine k phi. And there you go. Laplacian solved in cylindrical coordinates. Thank you guys for watching.